All right, so this is section 5.4, and this is the last section in chapter 5. And we are continuing looking at triangles and solving trig functions for different parts of the triangle. And so here I have that same information I had at the top of section 5.3, where we've got the definition of each of the trig functions, and we've got a right triangle, and if we're looking at different angles, angle A, and then side A, and so on. I also put these special right triangles that might be a helpful tool for us in this section. And I've generalized it so that it's not necessarily just in the unit circle, but this could be any size triangle. So if this side length is 5, for example, then in a 45, 45, 90 triangle, the two legs would be equal. They would both be 5. And then the hypotenuse would be square root of 2 times 5. And then similarly here with these different side lengths. So this next example here shows us a triangle, and the hypotenuse is 25, one of the legs is 24, and we don't know the other leg. So we can use the Pythagorean theorem, and I'm going to go ahead and label this x here. So we have x squared plus 24 squared equals 25 squared. And you might already know, if you observe this triangle and you know that this is a Pythagorean triple, you're welcome to use that fact here. You don't have to use the Pythagorean theorem, but I'm going to show you how to find it if you don't know that. And when we subtract 24 squared from 25 squared, we get x squared is equal to 49. So x is equal to 7. So we know all of our side lengths now, and we're looking at this angle T here. And we want to find all 6 trig functions of that angle T. So remember that sine is opposite over hypotenuse, so that would be 7 over 25. And again, we're working with just a triangle here. We're not in one of the quadrants on the coordinate plane, so we don't have to worry about positive and negative signs here. Cosine, if we're looking at angle T here, is adjacent over hypotenuse, so 24 over 25. And since we have those done, let's go ahead and do their reciprocal functions. So cosecant is 25 over 7, and secant is 25 over 24. Remember, tangent is opposite over adjacent, so that would be 7 over 24, and so cotangent would be the reciprocal of that, 24 over 7. Pretty similar to what we did in section 3. Number 2 has an angle of pi over 3, and it says, using what you know about the unit circle, evaluate all 6 trig functions. So sine and cosine, or sine and cosine here, are the ones that are around the unit circle that you should have memorized now. If at this point you have not memorized that unit circle with the coordinates around it, the angles in degrees and radians, that needs to get memorized now. If you don't have that done yet, it should have already been done. So make sure that you put the work in time to memorize that unit circle. So sine of pi over 3 is square root 3 over 2, and cosine is 1/2. And so we can go ahead and fill out these here. The reciprocal of 1/2 is 2, and the reciprocal of root 3 over 2 is 2 over square root 3. And we need to rationalize that, which we've done several times now. So hopefully you're getting comfortable rationalizing things. So we have 2 square root 3 over 3. And then for tangent, remember that's our sine over cosine. So square root 3 over 2 over 1/2. And I can multiply by 2 over 2. And that reduces out my denominators here. And I just have the square root of 3. And then cotangent is the reciprocal of that. So 1 over the square root of 3. And then again, I can rationalize that. So we have square root of 3 over 3 for cotangent, and that's all 6 trig functions at that angle. In section 3, we went over cofunctions, and we saw them with degrees. These are the same cofunctions that you saw in the previous section, but with radians here instead. So cosine and sine are cofunctions, tangent and cotangent, secant and cosecant. How we can apply it in a problem here is if I have sine of t is equal to 5 over 12, I can find cosine of pi over 2 minus that same angle. And what that's stating here is that if I have sine of some angle t, cosine of pi over 2 minus that same angle is equal to the exact same thing. So this would also be equal to 5 over 12. All right, in this next example, we have a triangle here, and we see that this is 30, this is 90. That means this has to be 60, and so we know that this is a special 30, 60, 90 triangle, and you can use those relationships on the previous page. The hypotenuse is going to be 2x. The short leg will be just x, and the longer leg would be x times the square root of 3. And if we know that this side length is, oh, sorry, I didn't realize you couldn't see that on the screen. Let me push that up there. So 2x, x, square root 3, and x, this is from the previous page in the notes. And we know this because if this is 30, this is 90, this has to be 60 because all the angles in a triangle add up to 180. So if x is this short side and we know that that's equal to 7, then 2x is going to be equal to 14. And we know that if x is 7, 7 times square root 3 will be 7 root 3 for our a value here. So we've found all of those unknown sides using that relationship. But if we didn't remember that, let's say we didn't remember those things. So we've already found the pieces that they asked for, the a and c, those unknown sides. But if we didn't remember that relationship, well, the other thing we could do is if we know that this angle is 30 and I know the opposite side, I could find sine of 30 degrees is equal to 7 over 2, or c, we'll just say c. And we know that sine of 30 degrees is equal to 1/2. So 7 over c is equal to 1/2. I could cross multiply. 1 times c is c, and 2 times 7 is 14. And that's exactly what we got using the other method. And then once I know c and I know this side here, I can use the Pythagorean theorem to find that missing side. But we've already found it. We already know it's 7 square root 3. All right, one more question in this section, and this is looking at angles of elevation and depression. So if I have a tower here, and let's say somebody is looking at the top, from the top of the tower, looking out, and this angle to the bottom here, this angle right here would be called an angle of depression. And then let's say there's a person here standing at the bottom or at the ground looking up at the top of the tower. The angle formed from the ground to where the person is looking to is called an angle of elevation. They're looking up. So in this next example, it says to find the height of a tree, a person walks to a point 30 feet from the base of the tree. She measures an angle of 57 degrees between a line of sight to the top of the tree and the ground. Find the height of the tree. So the nice thing is they've given us a picture here, and we can turn this just into a triangle without the tree there. This is 57 degrees. This is a right triangle. This is 30 feet right here, and we want to find the height of the tree. So I'm going to go ahead and call that x. So if I have the opposite side and the adjacent side, that would be tangent. So I can set tangent of 57 degrees is equal to x over 30, opposite over adjacent. I can multiply both sides times 30, and then I have x is equal to 30 tangent of 57 degrees. And this is not an angle we know on our unit circle, so that's something we can plug in our calculator. And when you plug that into your calculator, you want to make sure your calculator is in degrees. And we get 46.2 feet. So that would be the height of the tree. And that brings us to the end of section 5.4.